Okay, so now we are going to discuss about another data type which is called linked list. What is a linked list? So a linked list is also another linear ADT, abstract data type. Okay, this is how the linked list looks like. You have data which is uh, linked together. It's like a chain, and it could be a singly linked list or a doubly linked list. What does that mean? So okay. So basically, uh, let's say, okay, I think there is an example coming in the further slides. So there can be two types of lists: singly linked list and doubly linked list. Now, the uses in circular buffers or arrays, in chaining, in graphs. So this linked list will, for those of you who have not studied data structures before, linked list will be the first kind of data structure which will kind of introduce you to the area of data structures. Okay, an example is given here, a very simple example. There's a classroom which has got a single row, and Hari is sitting in the first bench. Suraj is sitting behind him, followed by Ram. So this could be modeled with a linked list. So you have Hari, then you have Suraj, this is Hari, then you have Suraj, then you have Ram. And in this way, you can model it. And if I ask the question, is Suraj sitting in the class? So what kind of operation is this? This is a search. You have Suraj, you will compare Suraj with the first element, the head is called the head element, head node. And this is not equal to Suraj. So okay, go to the next one. Is it Suraj? Yes. So answer is yes. I found Suraj sitting in the class. Then question is, who is sitting behind Suraj? Okay, I found Suraj. Now go to the next element. It is Ram. Okay, the answer is Ram is sitting behind Suraj. The answer. This question is also answered. Now next question. Next is Sham enters the class and sits behind Ram. Now you have to update your data structure to append this information that Sham is sitting behind Ram now. So okay, you start from here, go to the last, the end of, okay, you have to go to the Ram, you have to go to Ram, and after Ram, you have to um, make a new node of Shyam. Okay, so this is a node. A node means one entry of data. So what is, okay, what are the things? Now, whenever you see a data structure or data type, then you first think, what are the items what are the variables I need to have in this data type. For example, in a linked list, in a singly linked list, I need to, for every node, I need to store what is the information, what is the data in this node, and then what is the next node, the pointer to the next node. So you can see here, I have the data self dot. So I define a class called node, and this class has got uh, an instance, sorry, a variable called data. It's data is basically, it could be anything. It could be a string or a number or float, integer, anything. And then next is what? Next is the pointer to the next node, right? So now in a singly linked list, we have got multiple nodes. So see, earlier we had one node, and now we are defining a singly linked list. In this, we have got multiple nodes which are connected in a single pointer fashion. So you have the node Hari. So in a single linked list, we have a head and we have a tail. Actually, in doubly linked list also, we have a head and a tail. So head means the first node and tail means the last node. Now, head is a node, this one, and tail is a node, this one. Okay, so when you initialize a singly linked list, then when you initialize it, you give a single node. It has only single node, nothing is there. So the head is the same node. For example, I say, uh, let's say my S is equal to uh, singly linked list. and some n. What is n? N is a node. Okay, let's see what was my node and the data. Let's say it is Hari. Right, my n is the node Hari, and in the single linked list, I initialize it with the node n, and this node n becomes the head as well as the tail. Both head and tail are pointing to Hari. Now I have to append new elements, and we will see further what are the operations possible. So the next, okay, so given a singly linked list, how do I access the elements? For example, if I ask who is sitting at second position, let us say my POS is equal to 1, right? Second position means 0 and 1. So I have to define a function for traversing the linked list, and the outcome of this traversal, uh, I have to reach this particular location and then give the output or the data which is present at that particular node. So I start from the head, and so first my node is self dot head. Okay, so I'm sitting here. I start from here. This is my node and my node. Now I apply a for loop for I in the range of POS. So what is my POS? My POS, let us say it is given 1, right? So first my I is 0, and I say node equal to node dot next. Okay, okay, I think here the position is not starting from 0. Position is in this case it will be 2 only. Okay, so I start from my node is node dot next. Now I was sitting here, my node was here. Now node dot next, I move on to this position. So my n has been updated to this position. Now this is my node now, and then since my I was in the range 2, so now it will again go over. It will say for I, let's say my now my I becomes 1. Again this entry is I updated, so my node becomes this. This is my node. And now that's it. My loop is over now, and return node. So now this node is returned. I could return this node, or I could return the information in the node, but in this case, I am returning the node itself. Okay, you will see it has some uses. So that's why I'm returning node. So that's the thing. Now let us imagine if I give if position equal to 3. Okay, let's say if position equal to 0. If position was 0, what would have happened? If position is 0, then node was the head. Okay, node would have been here, right? My n is here. And then I in the range 0. This means this loop will not run, and this node itself is returned. So my head is returned. So I will get output as node only, no head only. My output will be the node containing Hari. Okay, now let's say if position equal to 5, what will happen in that case? Now, if my position is 5, then I start from the head node. I will run this loop how many times? 5 times, right? So I have to go. Yeah. So, okay, so I have to go to, from here, I will move on here, but as soon as I go here, there is no further thing to go. That's why when I do assert node dot next, when I'm reaching here, so here, this node dot next is none. So I have to raise an error that there is some problem here with this entry. So my algorithm, you can decide how to handle this error. So there is an error that my position cannot be 5 because my linked list is not of that length, is smaller than 5. So that's why you could either raise an error there, or you could return something. For example, just return the final node and saying that it's not possible, or means you have to raise a flag how you handle this situation that is either defined in the problem, or if it is not defined, you ask how to define it, or if it is still not defined, then you make an intelligent guess. So for example, in this case, I have simply raised an assertion error. An error is raised, no, it is not possible to achieve this position because this position is more than the length of the linked list. Now, so in this way, you will see here an error will be raised. Okay, so that is how I run my function. So whenever you write a function or a program, you always do some dry run with some example values of the input. Let's say if I give position 0, is it returning the head? If I give the position 2, is it returning RAM node? If I give a position 5, is it returning an error, or is it returning -1 or maybe none, something like that. So always check your algorithm in that way. Okay, now a traversal problem. I have to just print the entire list, whatever is there in the linked list, just print it. So how do I go about it? So define print list self. This is a function inside the class, so that is why self is here. So node is equal to self dot head. Now this is my node. My node is here. So I'm sitting here at the head, and then print node dot data. So whatever is the data is printed. I have printed Hari, and it says end with a comma. So I'm ending with a comma. Now next, I'm applying a while loop until my node dot next is none. See here, my node dot next will be none. So this is my terminating condition. Here it should stop. Okay. Now what happens inside the loop? I go to node is node dot next. So this is the node dot next is this node. Now this becomes the new node, right? I have assigned my node as this now. Now print again node dot data, which is Suraj. Comma. And then again the loop runs, and node dot next is none. No, node dot next is not none, but it is this node. Okay, so assign this node to my node variable, and then again print the data here, Ram, comma, right? And then again go here, check the condition. Node dot next is not none. No, it is none. So this loop will be terminated now, and print this. Basically it prints the next line. So you go to /n next line. So in this way you have printed your all the entries in the linked list. Okay, now inserting a new entry. This is an intelligent this requires some more deliberation. This is not very straightforward. So see how, let us say I am asking that I define a new node. Let's say my node is let's say the new node. The new node is node. What should the data here? The data is, let's say, Sham. So Sham. So this is a new node created. I want to insert it at position, let us say 0, 1. Let's say at 1. Let's say position is 1. Now I pass on to this function that this array dot insert new node comma position. Okay, so this is condition I will discuss later. Then come here. Assert position is greater than or equal to 0. Position is greater than equal to 0. Yes, because if I give a negative position, then it should raise an error because position is greater than equal to 0. Okay. Now if position is equal to 0, then this will happen. Our position is not 0. Okay, come here. Or else node equal to self dot fetch node position minus 1. Okay, so first of all, so position is 1, and this means I want to insert something here. I want to insert, let's say my output should be something like this. My output should be Hari followed by Shyam, because Shyam should be at position 1. So it should be Shyam followed by Suraj followed by Ram. Right? So that is why this should be my output, desired output. Now, what I'm seeing here is I will go to this node. Basically, I will go to this node. This is at position minus 1. And I will create a new node here. I will keep it here. Right? Now what I will do is, for this particular node, I will make a pointer to this node. Right? And then I will move this pointer to here. Basically like this, right? So see, that is the same thing is written in the code here. Node is equal to self dot fetch node position minus 1. So now my node is pointing to this one. This is my node. Right? This is my node. I should not make an arrow so that not to confuse you. This is my node. Now I'm saying new node dot next equal to next node. So I'm now making this connection. This is a new node dot next is node dot next. So this was my node dot next was this, and I'm assigning it to this new node dot next, right? So I made this connection now. Now I have to move this connection to here. So I'm saying node dot next. This is my node. Let me write it completely. Node dot next should be assigned as new node. So this new node is my node dot next. So earlier my node dot next was pointing to this node. Now I have made it point to the new node. In this way, the new node has been inserted here. Okay, so this looks like a very clean way, but this is a very important step. Please note it carefully, how we insert a new node. First of all, see, the order is important. If I would have moved this first without making this connection, then there is no way I can recover this, right? Because because that information is lost. I just broke this connection, make a connection here. Now, where do I connect this to? Because the connection is lost. So I have to first make sure without losing this connection, I first connect to it and then I connect. So what I'm holding, this is my variable node. This is my variable new node. These are two things which I'm holding. And if I break this connection, everything is lost. So please keep in mind that don't break this connection before you connect it to a new node, so that now if you break this connection, you still have this connection via new node. Okay, so please do this step very carefully. This similar thing will be used later also in many places. Okay, now come to removal. How do you remove a node? Okay, this is also something very carefully. How will you logically do it? Logically, what are the things you need to have in mind? Okay, so first of all, position is given to me. Let us say my position is 1, right? So what is my desired output? My desired output is Hari followed by Ram. So what do I do now? I have a connection only here, the head. This is my head. So I will say if position is greater than zero, okay, position is greater than zero, yes. Now previous node is equal to self dot fetch node pose minus one. Okay, first of all, I will fetch this node. This is my previous node as previous node as node at position minus one. This is pose minus one, right? So I got hold of this node, right? Now my next node is previous node dot next dot next. So previous node dot next dot next. So this becomes my next node. I've got hold of this one as well. I have saved it in a variable. So I'm holding these two things. Now I have to drop this thing. So what do I do? I will simply say previous node dot next is assigned a new value, which is next node. So this connection is established, right? Sorry. So when this connection is established, this connection is automatically broken, right? And this connection is broken, then see, there is no connection going back. It's only forward direction connection. So when this is lost, this is also lost. Now, so this information is removed. So my list now contains this, but still somewhere my memory is my memory in my RAM is still being occupied by this, but there is no way I can access this information, because how do I access? I have no variable which is connected with this data, this information. So now Python or any other language have automatic garbage collectors. When some information is not pointed to by any other information, so automatically that information is deleted. So this will be deleted automatically. But okay, for the time being, we can also manually delete it, but no, in generally it is automatically deleted by Python. So in Python, we don't need to worry about it. Okay, next. Okay, this is very simple to understand. Okay, now what will happen if my position is zero only, right? Because in that case, I don't have the previous node because it is already at zero. So what do I do? It's very simple. Simply I move my head to this location. Like earlier, my head was here. So let's say now this is a new use case where position equal to zero. What do? I simply move my head here. Earlier my head was here. Now I will move my head to this one. Right? That is automatically the zeroth node is deleted. So self.head equal to self.head.next. That's it. Now, if position is, let us say, what will happen if my position is very large? Let's say position is 5. What will happen then? Will my whole thing break? The answer is, when I will say fetch node at 4, then it will break. Means this function will do whatever it has to do. For example, it will either raise an assertion error or it will return none or something. But in our case, it is raising an assertion error. So in this way, it will say, no, there is some problem. This position is not allowed, right? So okay, this case is also taken care of. And now what about if position is some negative number? Let's say less than 0. What will happen? This condition will fail, this condition will fail, and this condition, it automatically asserts an error. It raises an assertion error saying that this position is not possible. So in this way, we see we have covered all possible inputs in all possible ways. So we have to be careful that we handle all the cases properly. Okay, I think in the previous slide in insertion, we should also do similar analysis. If I want to insert something at the head position, or if I'm inserting somewhere very far position, let's say at the 5th position, which is not there in the array, what will happen? So position equal to 1 is taken care of. Now let's come to an example, position equal to 0. What will happen here? What should happen here? A head will be inserted and everything else should move further. So what will happen? Position is equal to 0. Yes, this case. So I will say now I will get hold of my head. So new node dot next equal to self dot head. So I have my new node here. And my new node will point to head, right? First I made this connection, then I moved my head from Hari to new node. Then I moved my head, like I assigned the head as new node. I assigned new node as the head. Okay, so in this way, I have made my connections without losing any information. So that's now what will happen if my position is, let's say, negative. If position is less than 0, what will happen? So position is greater than equal to 0. Oh yes, so this will raise an error, right? If my position is less than 0, then this will raise an error. That so this is how I am handling this case, that I'm raising an error saying that position should be greater than or equal to 0. Now what will happen if position is 5, which is a very large number? If position is 5, which is larger than the length of the list, what will happen? So here, yes, so it will, this case, then fetch node will give an error saying that this position is not possible, right? This case is also handled. Now there is, okay, this function has another feature. Okay, if you're not mentioning the position, then it is just appending at the end, right? Appending at the end means you go to the tail and so go to the tail, assign the uh, uh, tail dot next is the new node and tail is the new node. Tail dot next should be none. Oh, okay, sorry. This is the current tail. So this current tail, this is the tail. So I'm making a connection to the new node and then saying that so it is like this. So let me use a different color pen. So let's say my position is none, this example. So I will say, first of all, I have my new node here. So my new node is here. And my tail is pointing here. Self.tail. Now what I will do is, first of all, I will make the connection. How do I make the connection? I will say this tail dot next is new node. Oh, I made this connection. Now I have to move my pointer tail to the actual tail because this is a new tail now. So I will just move this to this. So in this way, I have taken care of all possible situations. Okay. This was insertion. This is removal. Okay, now a comparison. Okay, just like in singly linked list, our node contains only a pointer to the next node. In doubly connected list, my node will contain a connector or a pointer, not just to the next node, but also to the previous node. So my node definition will be revised. So if you go back to the node definition, this node for doubly linked list will have data dot next, self dot data, self dot next, and also self dot previous. So you have got to, and similarly, all the operations have to be modified. Modified means you have to update not just the pointer to the next node, but also the pointer to the previous node. That is a doubly connected list. Now, what are the, how do we compare these two? They have their own advantages and disadvantages. Singly linked list uses less memory because you are just storing the information of the next node. You're not storing the variable of previous node. So you are saving your memory space. And also it has simpler implementation, because whenever you have an operation, you just update your next pointer. You don't have to update there's no previous pointer. But in the doubly linked list, you also have previous pointer which has to be updated. So it makes, you have to take care of more things, right? So that's a singly linked list has simpler implementation. Now, what is the advantage of doubly linked list over single linked list? The doubly linked list can be traversed in the backward direction also. So for example, I ask you uh, to uh, go to the previous node. In the single linked list, you cannot do that, because you have to start from the head and only move in the forward direction. You cannot go in the backward direction because there is no pointer to the backward direction. But in doubly linked list, you can do it very fast. So there are, depending on your application, you may require single linked list in some places and doubly linked list in some other places. Okay, now look at the complexity. In a single linked list, how does the search happen? So for search, you have to you have to go to each and every location. You have to uh, go to every location and compare with the key which you are searching in the entire list. So it is the complexity order n. Now, inserting at the head is very simple. Doesn't matter what is the length of the list. You just have the head. You just, new node has come, insert at the head. That is it. So it's a constant time complexity. Inserting at tail also, you have the pointer to the tail. Just insert there. So order n. Now, inserting at any other position, it is of order. And why? Because you have to traverse the whole list one by one. You have to actually go to every entry, right? Because our access, remember, our access is not possible. It cannot make a direct jump to that location. It has to go through each element. That is why our insertion as well as access both have complexity of order n. Now remove at the head. If I have to remove the head node, what is the complexity? Constant time complexity, as we have seen. Now remove at any other position. If I first have to go to that position, which means I have to do n steps or do that many nodes I have to traverse. That is why the complexity is of order n. Now removal at tail. This looks strange. Why should removal at tail be of complexity n? Because you have the pointer to the tail. You just have to remove that. No, but you know why? Because you have to then update your tail pointer to tail -1. Like whatever was the last tail, the previous one now becomes the tail. So to update your tail pointer, your tail variable, you have to actually again start from the head and go to the node which is just before the tail. So that is why the complexity is n there. Now, okay, so that's it. In the next video, we will see stacks and queues.